Oh, hi there. Welcome one and all to topic 7, which is trigonometric functions and cyclical graphs. We're going to be looking at things called sinusoidal functions. And these are the functions that are based on the graphs of y equals sine x and y equals cos x. So these two are parent functions that we're playing with. And we can get some exact values for these functions if we want. If we want, we can use special triangles or unit circle to figure out some exact values here. Like we know that sine 0 is 0, sine pi over 6 is 1/2, sine pi over 2 is 1, and then of course the rest of these here. And by using these inputs as our x values, we can take these results on the other side of the equal sign as our y values, and then graph this thing, which then looks like this. So one thing worth noting is that the range of the function goes from -1 to +1. So at the very lowest, we're down here. At the very highest, we're up here. And we never exceed that. That's something we're kind of familiar with in terms of what is valid, what isn't valid when we're, say, solving a trig equation. One other fun thing is that this function actually cycles. So when we look at the sine function, and there it is in all its glory. There it is, and it just keeps going in a continual wave, up, down, up, down, up, down, up, down. It does that forever, ever. And that, of course, is because of coterminal angles. So since we have a coterminal angle every 2 pi, we see that this repeats every 2 pi. That it peaks at pi over 2, and then 2 pi later, at 5 pi over 2, it peaks again. Add 2 pi to that, you're at 9 pi over 2, and you have another peak. And the shape just repeats on and on and on. So here what we see from 0 to 2 pi is the same as what we see from 2 pi to 4 pi. And that's the same as what we see from 4 pi to 6 pi. And of course, so on and so forth. And of course, we'll also see that in the negative direction, from -2 pi to 0, from -4 pi to -2 pi. So we have that period, which in radians is 2 pi, or degrees, 360 degrees. There's a number of features we can discuss. We did already talk about period there. The amplitude is how high the wave rises above its middle area, or how deep it sinks beneath that. So looking at this, we've got a middle line here. This one is situated right on the axis. And the curve rises 1 unit above that. It sinks 1 unit below that. So that is our measure of what's called amplitude. We can find it formulaically, as is stated in the notes. It's maximum minus minimum divided by 2. And we'll see later on when we're given equations, we might have a faster way to get there. So the amplitude of a regular sine wave is 1. Maybe that gets modified as we have transformations. Now the cosine function is very similar. It's just offset a little bit. So when you have your cosine function, boop, right, that starts at 1 because cosine of 0 is equal to 1. Cosine. Nailed it. So we see the cosine function is just like the sine function, but shifted a bit to the left. You can actually say that one's the other with a transformation. But it has that same range of -1 to +1. It has that same period of 2 pi, again because of those coterminal angles. We're going to be transforming these functions in all sorts of ways, as we've been doing throughout this year with other functions. So we're going to be stretching it vertically, horizontally, or compressing it. We're going to be shifting it up, down, left, right. You could say that we're also reflecting things, but when you reflect it, that can also be done through just shifting the graph left or right a little bit. So we won't really focus on reflections so much. They're not quite as relevant for sinusoidal functions. Right now, we're just going to look at the effects of stretches and compressions on the amplitude and the period. Whee! So let's start with just the amplitude and what happens there. Here we have y equals sine x, we've already noted that the range is from -1 to +1. So we know that the minimum is -1. We know that the maximum is +1. And we also know that the amplitude is 1. How does that change when we have something like 2 cos x? Well, if f of x is equal to cos of x, then over here we've got 2 f of x. And from our knowledge of transformations, that means that we have a vertical stretch factor of 2. What does that do to everything? Whoop, whoop. We know that that's going to multiply all our y values by 2. So our range now, instead of being -1 to +1, is -2 to +2. So we have a minimum value. It was -1, but we multiplied that by 2. We have a positive value. It was +1, but we multiplied that by 2. And for the amplitude, if we take this formulaically, we can say it's max minus min divided by 2, just pulling on that same formula that's on one of these pages. Whoop, there it is. And as a result, 2 minus -2 is 4, divided by 2 is 2. Neat. Take a moment, try the others. There's, 2 more on this page, and then we'll talk about the general rule and move on. Oh, this is me pausing. This is me moving forward. So the range of this thing, since we multiply by 7, takes us from -7 to +7. We've got a minimum value of -7. We've got a maximum value of +7. And what is our amplitude? Well, we've got 7 minus -7, and then that's divided by 2. That gives us 7. Wow, mysterious. And this last one, again, our range is normally -1 to +1, multiplied by 24 here, means we're going from -24 to +24. So we've got a minimum value of -24. We've got a maximum value of +24. And then our amplitude, which is still max minus min over 2, is going to be 24 minus -24, all divided by 2, which gives us 24. And we're probably detecting something here. We had 1 sine x, it went -1 to +1, had an amplitude of 1. We had 2 cos of x, went -2 to +2, we had an amplitude of 2. For 7 cos of x, we had amplitude of 7. For 24 sine x, we had amplitude of 24. So we can make a general statement. The amplitude of that sinusoidal function, when it's been vertically stretched or compressed by a factor of a, is just a. So if we're dealing with like 373 sine x, there's the amplitude, 373 right there. Or even if you're dealing with something else, like 1/8 sine x, your amplitude is 1/8. So that a value is always your amplitude. You can remember it because amplitude starts with a. Let's look at horizontal transformations a little bit too. And again, just kind of stretches and compressions. Here we are going to actually describe what's going on. Woo! So we'll describe the transformation. What does this transformation look like when it's applied? And then we'll look at its effect on the graph's period and state the period of the function. So this first one doesn't have any transformations, just a basis here. We know that the period, and we can use a big old capital P for that. We can say that the period is 2 pi. And that's the period of all of our base sine and cosine functions. Over here, if we're pretending that y equals, if we're pretending that f of x is equal to sine x, then what we've got here is f of, not bx, but 2x. And there's that kind of equivalence, which means we have a b value of 2. What does that do? That's right, it causes a horizontal compression. My goodness. Don't mind me. So we've got a horizontal compression factor of 2. That means that all horizontal aspects are going to be squished by a factor of 2. The period is a horizontal measure. That means we'll be dividing the period by 2. The period was 2 pi. We're now dividing that by 2. So the actual period is pi. So for this function, the period is equal to pi. Try the other couple on this page, see what happens, and then we'll make our general rule. Well, I don't know about you, but I paused, and now I'm resuming. Here we've got a horizontal stretch. Which means we're going to multiply the period by 3. We could also phrase this a different way, just to be more consistent with what we said above. Here we said we divide the period by 2, we divided by that b value. So similarly here we could say that we're dividing the period by 1/3. And it's this kind of second definition, the division one, that I'll focus on. Because we'll say we have 2 pi divided by 1/3. And when you do that operation, you end up with a period of 6 pi. You'll get that either way, whether you multiply by 3 or divide by 1/3. Of course, they are the same operation, realistically speaking. But it will lead us to our general rule. And this last one, whoop. Got a horizontal stretch by a factor of 8. You could say that we're going to multiply the period. I'm just going to phrase it. That way. Divide the period by 1/8. So then your period, which is normally 2 pi, is getting divided by 1/8, which is 2 pi times 8 over 1, which is 16 pi. As a general rule, what we can notice is that we always divided by b. We divided by b, we divided by b, we divided by b. And the period is thus always 2 pi over b. Or if you want that in degrees, it's 360 degrees divided by b. So when we actually look at these functions, let's just throw an a here because we can, and let's throw a b in here because we can. As we see a increase, we see that function's amplitude go way up, or we can get it to shrink down, 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 down. Tiny little wave. It's so little. So we see that effect happen with a, and then b. As b increases, this graph gets real squishied in. Whoa, look at all them pile in there. But as b lowers, they start to spread out. And there it goes. Whoop. There it is. So those are the effects we should be anticipating seeing. You get high b values, you get a big squish. You get high a values, you get real stretched out up down like. So just be aware of what effects those kind of have. Anyways, we're going to put these together. Whoop! On this page. So on these ones, you're just going to state the amplitude and period of each function. If you want, I can start this off. Here I will say that the amplitude is 2. It's just straight up that a value. Nailed it. And then for the period is 2 pi over b. So that's 2 pi over 4, which is then pi over 2. So every pi over 2, this function repeats itself, and it does exactly what it was doing before. Or 2 pi, it was doing exactly what it did pi over 2 ago. There are some more on this page. Whoa! So try those other 7, and then play this video again to see where you're at. I will, of course, begin. Amplitude is 1/2. The period is 2 pi over b. So that's 2 pi over 1/2, which means we have a period of 4 pi. And again, if you want to see that in action, whoa, let's change that to cosine. We had, this was 1/2, and b was also 1/2. And we can compare that to the regular cosine function. So we see the difference there. Right? This green one happens a certain frequency, and then the black one, the transformed one, is kind of squished down vertically and stretched out horizontally. We really pulled it apart there. Look at it go. Man, sinusoidal functions are dope. You can see all of these in Desmos, of course, and I'll just make a point about that in a moment or two. But let's finish these examples first. The amplitude is 8. And the period is 2 pi over 3. Oh, that's as simplified as that gets. Your amplitude here is 14. Your period is 2 pi over pi, which is 2. Interesting. That was a weird one. Amplitude here is 5/3. The period is 2 pi over 2/3, which all in all is 3 pi. Zip. Your amplitude is 84. The period is 2 pi divided by pi over 4. So the pi's cancel out. We just get 8. Just a couple more left. The amplitude is 94. The period is 2 pi divided by, whoa, that b value is 2 pi. Weird. And there's this last one. The amplitude is 1/40th. The period is 2 pi over 8, which is just pi over 4 when we simplify. So there's all the answers on screen at once. There is some practice work down here. Definitely worth a look. Numbers 4 to 5, the graphing is optional, but I recommend giving it a try. Whenever you kind of want to get a feel for what a function looks like, and you're like, I really wish I had a visual for that, feel free to just use Desmos here, same as I did. Just one pro tip is with the scale, under your settings, you'll probably want to just make sure that the x-axis steps by pi over 2 or some fraction of pi. And that it might depend on your period a bit. So if you know that your period actually doesn't involve any pi's, then maybe you don't want your step to be that. But you'll have to gauge it accordingly. If you have questions, comments, concerns, of course, do make sure you let me know. Message me via Teams or send me a fax or something, and I'll respond. Other than that, I hope you had a most lovely time, and it's now time for this wave to wave bye. My jokes are terrible. The end.